Okay, so we are going to start some notes here, and what we're going to talk about is the evidence for evolution. You got a good intro from Stated Clearly, I think. So what I want you to remember when we're talking about evidence, how many of you have heard the words evidence and claim in English? Claims and evidence and explanations? Okay. So the claims, I think, Stated Clearly, did pretty well with. That all living things on Earth are related, and that the fact that we have 8.7 billion species that are all related was driven by some natural force. Does it drive anybody nuts that that's crooked? Yeah. Sorry. Here. So when we're talking about the theory of evolution, I want you to remember three sort of foundational assumptions. So the assumptions that we are starting from is that first of all, that the Earth is really old. 4.5 billion years roughly. And you guys did some timelines. You're familiar with a little bit of that Earth history. You know that organisms of some kind have been on that Earth for most of that time. This is what we're claiming. And what the theory of biological evolution claims is that all the organisms we see now, all 8.7 million species roughly, evolved from those early single-celled organisms. With this little claim. And this one is not part of the theory of evolution. This is actually a geology claim. But how do we know the Earth is 4.5 billion years old? How?
The rocks.
The rocks? What about the rocks? Do they have dates stamped on them? Fossils, carbon dating. How do we know that, have any idea how old Earth is?
Rock formations.
Rock formations. What about rock formations?
Layers.
Layers. What about layers? Those are great answers. Those are right. Those are good. So we're going to back up a little bit, and we're going to talk a little bit about radioactivity and how we tell how old rocks are and how we tell how old Earth is. So what does it mean if we say something is radioactive?
It's radioactive. I can't think of the word else to say.
It's unstable.
Unstable. Give me more words. Toxic. What else? Deadly. What else? Poison. What else?
Medicine.
Medicine. Okay. What else? Yeah, we use radiation medically.
Yeah. Light. Because light gives off radiation.
Different kinds of radiation, but okay, not the kind we're talking about. But no, there are types of radioactive materials that are used medically. Okay, what else do you think of when I say radioactive? Huh? Nuclear. Okay. What else? I like that word. I should write a few of these down. Okay. So, somebody said unstable. I like unstable. Good. Unstable's good. So, we're going to talk about radioactive materials for a minute. And would you all be shocked or horrified if I told you that there were radioactive materials in this room?
No.
You're all radioactive. Did you know that? Radioactive, doo-doo-doo. Radioactive, doo-doo. Nobody? Darn it. I need a more contemporary song, clearly. But anyway, yeah, you're all radioactive. So's the ground outside, so's a banana. Not a big deal. Now, you shouldn't go out and eat radioactive materials that are strongly radioactive, but background radiation is pretty normal. You all are carbon-based life forms. Have you heard yourselves called that before? Okay. Looks kind of like Charlie Brown, but his head exploded. Actually, there is a striking resemblance to Charlie Brown. So here's my sort of generic person.
Is that hair, though?
Yeah.
Okay, I was just wondering.
Yeah.
I didn't know if it was a detail that didn't make
No, it's hair. You can draw your person bald. So, you're a carbon-based life form. So's a rabbit. So's a maple tree. So's an earthworm. So's a fish. So's a bacteria. So's a dandelion. So's a deer. So, actually, every living thing on this planet is a carbon-based life form. Every living thing we know of on this planet is a carbon-based life form. You and every other member of this living things on Earth kind of family. So, you're made, why do we call you a carbon-based life form? You're largely made of carbon. Carbon is one of the 6 elements that makes up most of you. Carbon, nitrogen, oxygen, hydrogen, sulfur, and phosphorus. 6 elements make up pretty much all of you. 6 kinds of atoms make a glorious mammal, bipedal creature such as yourself. Bipedal meaning walking on 2 feet. It's amazing. And guess what kinds of things you can use for food and get nutrition out of? Rocks? Can you eat rocks and get nutrition out of them? No, you can't. It has to be things that were once alive, because it has to be other carbon-based life forms. The kinds of chemicals your body needs are things that have carbon in them. So, draw a little badly deformed apple here. There we go. It's just a little lopsided. It's fine. Guess what that apple's made from? Carbon. It's a lot of sugar. And sugar is made up of carbon, hydrogen, and oxygen. And your body takes that carbon and those other chemicals and uses them to power your cells, run everything, build new structures. Cool. So here's the weird thing about carbon. There are 2 different kinds of carbon on this planet. There are actually 3, but we're only going to talk about 2. There is carbon-12, which has got 6 protons and 6 neutrons, and it has a mass of 12. And then there's carbon-14. 6 protons, because if it didn't have 6 protons, it wouldn't be carbon. 8 neutrons. How many of you remember where do we find neutrons and protons in an atom? In the nucleus. Center of the atom. Electrons are circling all around. Well, here's the thing. 99% of all the carbon on the entire planet is carbon-12. 99% of the carbon atoms in your body that make up your DNA, that make up your skin, that make up your hair, that make up your muscles are carbon-12. About 1%, and I could be getting the numbers wrong, but you know, somewhere in there, a small amount are carbon-14. And as long as you are taking in carbon, if you are eating plants or animals or former animals, anything that contains carbon, which are all the things you can get nutrition from, you can eat bugs, you can eat corn, you can eat venison, you can eat potatoes, you can eat anything that grew on this planet, or grew up on this planet, and you're going to be taking in 99% carbon-12, 1% carbon-14. So here's my question. When do you stop taking in carbon? So I passed this dead raccoon on the road this morning. Think he's taken in, oh, he was smushed. Think he's yeah, exactly. That raccoon has no further need of taking in carbon. That raccoon is not taking in any more carbon. When you die, you stop taking in carbon. And at the point when you stop taking in carbon, you're sitting at 99.1%. But here's the thing. Because carbon-14 is radioactive, it does what we call decay. It breaks apart, and it loses neutrons, and it becomes carbon-14. So if we had a sample with a known number of carbon atoms, we could look at the percentages of carbon-12 and carbon-14 and tell how long something had been dead. It's called radiocarbon dating. We use this same idea, it's called radiometric dating, radioactive dating, with rocks. And a few of you kind of, I think, knew a little bit about this. But there are rocks that have similar kinds of chemicals that break down and change into a different chemical. Remember, this is all about the nucleus. We said that, we said that protons and neutrons all hang out in the nucleus. And they do. And when we get a really crowded nucleus with a lot of them, has anybody here had a crowded family gathering ever? 20 people in one house, one turkey, maybe one Christmas tree, maybe one table, too many cousins, too many aunts, too many uncles, too many dogs, too many kids, too many everything? Yeah. At that point, anybody ever feel like they just need to get out for a little while and go take a walk? Okay, you people, this is great. I'm leaving you all now. I'll be outside if anybody needs me. I'll be out behind the barn looking at trees. I'll be out going for a walk down around the block. I'll be out, oh gee, I think I have manure to shovel. Right now, I need to go. I just need to escape for a little bit. When it gets too crowded, it gets a little unstable, don't you think? Well, here's the amazing bit. The nucleus of an atom is no different. And especially when we get really large nuclei, they tend to get a little bit unstable. And they tend to lose chunks. And some of them will lose just neutrons. Ping! 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 Over time. And that means they stay the same element, but they change their mass. Because neutrons don't change the element, they just change the mass. But some of them, you get those guys back in place, will actually lose what are called alpha particles. And somebody even said the word alpha particles. Boing! Alpha particles are big. They're heavy. They'll do some damage. Alpha particles, if you get hit with an alpha source, it's very probable carcinogen. Causes cancer. You don't want alpha radiation. So, boing. Those are actually changing the chemical because they're losing protons. We have rocks in the Earth's crust, and we can, if we look at the chemical makeup of these rocks, we can actually tell how long it's been since those rocks formed, since they cooled. So based on that kind of evidence, we can say with, scientists never say 100% certainty, but we can say with almost 100% certainty, yep, Earth is about 4.5 billion years old. We know that. And it's all based on chemistry and geology. And we've looked at Earth rocks, we've looked at moon rocks, we've looked at a lot of rocks. So, we say that organisms of some kind have been here most of that time, and that the claim of the biological theory of evolution is that we all descended from single-celled organisms. So what's the evidence for that claim? So what was one of the types of evidence that was discussed in the film? Give me one. Pardon? Give me one of the kinds of evidence that he discussed in the film. Good old Mr. Perry. Genetics, okay, they did some DNA analysis. We'll look at some of that. But the one that we're going to talk about first is actually fossils. We're going to start off talking about the fossil record. And what the fossil record is this idea, it's this collection of fossils that we put them together, we line them up, we can tell how old they are, and we see that they show gradual change towards animals that look like modern animals, and plants, and other things. And I chose this image because I thought some of you might get a kick out of it. Anybody know what kind of animal this is? It's a horse. This is a horse, and this is actually the sort of fossil progression of horses from this little tiny, what's called Eohippus. 50 million years ago, there are fossils of this little teeny tiny Eohippus. 38 centimeters tall. Do you know how tall 38 centimeters is? Oh yeah, they're extinct. There is that. But other than the fact that they're extinct, they're adorable. They're all dead. Yeah, they probably did. They were a wild animal, and horses can bite and do a lot of damage. Yeah, they probably had a heck of a bite, for something that's less than, not as tall. So we find fossils from 50 million years ago of this little tiny creature. Now, how do we know that this is related to a horse? Because this doesn't look a whole lot like this. And these bones don't look quite like these bones.
There's a resemblance.
But when we look at the whole history, when we look at changes between this one and this one, it's not a big change. They're different, but it's not a huge change. And when we look at this one to this one, they're not the same. They are different, but they're minor changes. And then when we go from this one to this, again, minor changes, but clearly related. And we see the same thing with the skulls. And we talked about the fact that skulls are a real important identifier when we're looking at fossils or just animals in general. So this fossil record shows this progression. Now, there is not a fossil record for all species. Some species have an excellent fossil record. Horses have a great fossil record. We can look at very early animals and know clearly that they're pretty related to the horse. Canids, like wolves and dogs, have a pretty clear fossil record, a pretty good fossil record. A lot of fish and aquatic animals have good fossil records. Birds have a great fossil record. Not everything does. Not everything leaves a good fossil record. We're going to talk a little bit about why that is. Who here has seen a fossil? Awesome. When we go to the museum in the spring, the Carnegie Museum in Pittsburgh has got one of the best dinosaur fossil collections in the country. And it's an hour and a half from our doorstep. Cost of the field trip is usually between $20 and $25, and we had a good sub sale, so we should be able to keep it. We try to keep it under biology and chemistry. Yeah, biology and chemistry. It's optional, but I would encourage you to go if you get a chance, because it's an awesome place, and you won't get another chance probably to go that cheaply, and to go, sort of where somebody's taking you there. It's awesome. It is phenomenal. Yeah, it's Carnegie Museum of Natural History in Pittsburgh. It's awesome.
Yeah, I've been there. When do we go?
It is. I love it. In the spring, usually in April. Okay, so what is a fossil? You people say you've seen fossils.
It's a indent on like a rock.
A rock? Okay, what else do we have here? Survey says a rock. Survey says clay. Bones.
Yeah, that's what I meant. Not
I think
that word.
imprinted in stone. Okay. Or imprinted in stone or clay. What else do we have? What's a fossil? So imprint in stone or clay. Maybe you want to add to that? Go for it.
Bones that turn into rock.
Ooh, bones that turn into rock. Ooh, I like that. Petrification. What else? Anything else classify as a fossil?
They have leaves that are like.
Poop! Oh, I love fossil poop. It's so cool. Do you know what dinosaur fossil... No, seriously, it is. When we go to the Carnegie, you can touch fossilized dinosaur poop. Touch, touch, touch. It's so cool. Oh, it's awesome. It's called a coprolite.
How does it?
Yes. So, what are fossils? They're either actual pieces of organisms or impressions, that's the word you were going for, left in rocks by organisms. So they're either actual pieces of the organism, and sometimes that can be bones, sometimes it can be bones that have mineralized and sort of turned into something rocky. Sometimes it's just a print left by a bone. You can get a whole critter in amber. I'm actually wearing amber earrings today. I wore them on purpose. And fossils tend to form when organisms get buried. So the most common way for them to get buried is fine sediment. So we tend to get fossils out of swamps and lakes and streams. Volcanic ash is great for making fossils.